So today the lecture is about potential and congestion games. These are very important classes of games. We are always going to talk about the normal or strategic form description and simply that these are the classes of games we are going to study. So intuitively speaking, potential games are games where all the players have a common goal. And usually such games are not studied at all at the basic course. Usually the games which are studied at the basic course are in a way orthogonal to potential, namely constant sum or zero sum games. Because in the constant sum games, all the players are rivals. So they actually have exactly opposite goals. I think, however, that both classes, potential and zero sum, are very important. Indeed, zero sum was studied, I think, by von Neumann originally, so they were studied many years ago, and their theory is more classical than the theory of potential games. We, of course, we will study that too, but we first start with potential games. And our congestion games, they are another, you can say, another description of the class of potential in games, but the idea there is different. The idea there is that we have several participants, and the congestion means that they all use the same resources, and the more the same resources used, the less efficient it becomes. So that is also a very important class of games. It simply happens that such games are potential, and moreover, all potential games can be shown to be isomorphic to congestion games. That's why this should be studied one together with the other one. Now, the idea of potential is common in physics, of course, and also in analysis of algorithms. So when you can find a function which shows something that is like one function that shows something about other actions, let's say in algorithms, or which shows what a certain body can, which energy the body has to perform some action, for example, in physics. So the idea of potential, that you have one function which describes the system, is also what we have here. And we are going to see some similarity to physics, actually. Of course, it's not exactly the same. We never can say that is how it is in physics, and therefore we are going to make it here. But there is a lot of commonality. Moreover, actually, there is even something which is about related to decomposing games to potential and so-called harmonic games, but that is beyond the scope of our course. Now, the idea of congestion games is very common in many applications. Of course, as you can see, there is this idea of road congestion, but there are many other congestions. We can speak about students who study at some place, and the congestion here is how many people sit at the same room. There can be congestions when any resource, for example, bandwidth, in the case of mobile phones or something like that, any resource which is in a way limited can give rise to this congestion game. So this is the basic intuition, I would say, not even the agenda. The agenda is as follows. Having introduced the topic, we are going first to talk about potential games and their amazing, in a way, properties. By the way, those games, they rise in many other contexts. So sometimes you study something else, and then you can prove that if the game is potential, then certain nice properties hold. So first we're going to define varieties of potential games. Potential games, I just call them potential games, but I mean actually exact potential games, but there are many weaker definitions. So wider classes when you require less, and despite that they are less nice, but of course they are wider, and therefore maybe they're we can use them in for games for which we simply cannot use the laws of potential games because they are not potential. So it's important to describe the several varieties and to exactly tell which properties each class of games has. We are going to exemplify those varieties, see how the idea of potential relates to Nash equilibrium, how the idea of potential relates to finite improvement property, so that at some point it's impossible to infinitely improve the utility of at least one player, and therefore this is the idea of finiteness, as of course that is related to having a Nash equilibrium in a way. Then we are going to bring equivalent definitions for potential games. Actually, we are going to show a physically inspired definition for potential games. And finally, we are going to say that actually potential allows us to define a certain refinement of the set of Nash equilibria. Of course, sometimes you have only a single equilibrium, but in general you may have many, and therefore we may need to define a more interesting set than just a Nash equilibrium. And then we're going to talk about congestion games, so having shown some practical examples, we will speak about these isomorphisms with potential games, which is quite remarkable, quite amazing. So let us start with the potential games, and we're going to start with the widest class of games and in this family of classes, and then we're going to converge to the narrowest class, which is potential games. So the widest class is generalized ordinal potential games. So it's not even ordinal potential, but it's also generalized. It's the most generalized class we will study. And here, given a strategic form game, I remind you that it is a game which has a set of players, a set of strategies, which is a Cartesian product of the strategies of each one of the players, and a set of utility functions. Now, a utility function is a function from the set of strategies to the real numbers, telling what is the utility of a given player given this strategy profile. A potential function, or a function, sorry, from the same set, from the set of all the strategies profiles S, also to real numbers. So the domain and the range are exactly, and that I think that it's yes, the domain and the range, they are exactly defined as they are for any utility function. Such a function, in a way, should kind of represent all the utility functions. That's the idea of a potential. And formally, a function P from the set of strategies to the set of real numbers is a generalized ordinal potential if for each player, for each set of strategies of the other players, and for each two strategies of this player I, if we look what is the utility gain that the player I obtains from changing from TI to SI, when the others keep doing S minus I, then that utility gain of the player who changes, if that is positive, then also the utility gain of the potential function with the same argument is positive. So it's not the same, but if player I gets a positive utility delta, so if player increases her utility by changing from TI to SI, then the potential function also increases when the profile changes from TI and S minus I to SIS minus I. So that is the weak, admittedly, because we begin with the weakest definition, to allow for a wider class of games. But that is the idea of the potential function kind of modeling the changes in utility. And please pay attention that there is one potential function, but that condition is true for all the players. And if a game admits such a potential function, that such a game is called a generalized ordinal potential game. So a game admitting a generalized ordinal potential function is called a generalized ordinal potential game. And as I already said, the intuition is that the sign of how the utility of the player who changes, whether it grows or strictly decreases, it implies what happens with the potential. That's the dependency. Another class of games, now we are going to make this class a bit narrower, to narrow down a little bit, is called ordinal potential.